Kia ora, Year 12 and 13. This is the last part of question 3 of the 2014 complex numbers paper. Alright, the first question is a merit question. We're given a complex number z, and that's in rectangular form. So z is equal to 3 plus 2i. We have to figure out the value of its conjugate squared plus 1 over z squared. Alright, so nothing particularly tricky about this. We've just got to get on with it. So I'm going to do that in a couple of separate steps. So the conjugate is 3 take away 2i. Right, so I'm going to chuck in a little bit of geometry here just to do it along the way. Right, you're not asked for this at all. But z is going to be out 3 and up 2. So that's z there. And its conjugate is the reflection of that in the axis. Okay, so if you're thinking of it like this, that's z and that's z bar, or the conjugate. Okay, and it always works like that. So let's look at squaring the conjugate. And this is what we're going to get. 3 minus 2i squared. So I'm going to expand that out. Some of you won't need to do that line, but most of you probably still will. So here we've got 9 minus 6i minus 6i, so minus 12i. So that's that bit done, and that one done. The last bit is minus 2i times negative 2i times negative 2i, which gives me 4i squared. So I'll put that in like that. Right, but that is equals 9 minus 4, so that's 5 minus 12i. Okay, so that's my conjugate squared. But I'm doing the working for the two bits separately because you know that this bit here is going to involve multiplying by the conjugate of the bottom line of the denominator, so I'll just split it out into two bits. So that's the first bit. I'll do a new slide now. So what's z squared? Well, z squared is 3 plus 2i squared, and that's equal to 9 plus 12i minus 4 again. So that equals 5 plus 12i. So now we can put it all together. Z conjugate of z squared plus 1 over z squared is equal to 5 minus 12i plus 1 over 5 plus 12i. That equals 5 minus 12i plus 1 over 5 plus 12i times the conjugate of that, which is 5 minus 12i, and the same up here, so that I don't change the value. Right, so simplifying that, I'm going to try and I'm not going to squeeze this in, I'm putting a new slide in. Alright, so we've got, carrying it over, 5 minus 12i plus 5 minus 12i in the numerator times this in the denominator. Right, and we're going to get our familiar pattern, which is 5 minus 12i plus 5 minus 12i divided by 25. It's those. This times this, take away this times this will disappear. That's the whole reason we do this. And then I've got plus 12i times negative 12i, which is going to give me plus 144. Okay, so we're nearly there. So this is 169 times 5 minus 12i plus 5 minus 12i, all over 169. So don't ask me why they picked such hideous numbers, but they did. Right, so when we expand all of this, we end up getting 850 over 169 minus 2016 over 169i. Now, if Patty is listening, Patty, I can just about hear you asking me if decimals are okay over YouTube. Yes, they accepted decimals in the schedule here, but I wouldn't round too hard. I would leave in 3 or 4 decimal places. And as you know, I'd rather you stuck with fractions. Okay, on to the next question, which is the excellence question. Right, so we've got alpha, beta, and gamma are the roots, 3 roots of this cubic equation here. and we're told that they're real numbers. So there's no complexy number part in here really, it's just a wee bit of algebra. So let's write down what we know. We've got ax cubed plus bx squared plus cx plus d equals 0. And we can also say that these things are the three roots of that equation. So right at the outset, I'm going to just divide everything through by a, so that I've got an x cubed. Now I don't have to do it this way, but that's how I'd think about it. It's always nicer, or just about always nicer, to have your coefficient of your leading term being 1. Right, so that's what we're working with. That's an expanded form. But we know that alpha, beta and gamma are the three roots. So we know that this is true as well. X minus alpha times x minus beta times x minus gamma equals 0, because that's what it means for something to be a root of an equation. So what we're going to do now is just expand this, and then we're going to match up the coefficients, and we've seen that technique in quite a few other places. So expanding here, we're going to get x cubed minus, well, let me go a little bit slower. I'm going to leave the x minus alpha, and I'll expand these last two brackets here. So x squared minus beta x minus gamma x plus beta gamma, and that equals 0. And now on the next slide I'm going to do the same thing, just multiplying this right through by all of this. Okay, so now I get x cubed minus beta x squared minus gamma x squared plus beta gamma x minus alpha x squared. I'm just going to stop talking and keep writing. Okay, so there you go. So all I'm doing is I'm expanding a cubic. There's nothing really to it. What I'm going to do next is collect up like terms. So x cubed minus alpha plus beta plus gamma x squared. Right, so that's that one, and that one. Now I'm going to collect up the x terms. So that's going to be plus x times alpha beta plus beta gamma plus alpha gamma. It's those three. And lastly I'll have minus alpha beta gamma. So let's look at what we had when we had it in expanded form. Well, we had x cubed plus b over a x squared plus c over a x plus d over a equals 0. And I've lost the equals 0 up there. There you go. Right, so that means that this must equal this. So we get b over a equals negative alpha plus beta plus gamma, or negative b over a is equal to alpha plus beta plus gamma. So that was the first thing we were asked to show, and we're going to do the same thing with the next two. This one here must equal this one here. Right, and lastly, this one here must equal this. Right, so we do the same thing. I'm actually, for once, I'm not going to write all of that out because I think you can do that and you're just following through. So now we've proved the first three things, so we've finished part 1. Right, so the last thing we're asked to prove is that alpha squared beta gamma plus alpha beta squared gamma plus alpha beta gamma squared is equal to BD on A squared. Now that looks awful if you're looking at that side, well, kind of awful, but if we look at this, we can split this up like this. So BD over A squared is just B over A times D over A, which is the same as negative B over A times negative D over A. You might be wondering, why on earth have I put those negatives in? Well, it's because of what we just showed in part 1. We know that negative b over a is equal to alpha plus gamma plus delta plus gamma, alpha plus beta plus gamma, times this one here we know is alpha beta gamma. So if we expand that, we get alpha squared beta gamma plus alpha beta squared gamma plus alpha beta gamma squared as required. Okay, so it's another example of an excellence question in complex numbers that I don't think is as difficult as some of the ones you're going to see in differentiation or integration. You just have to remember what the different things mean, what it means to have roots of an equation, and then just proceed to expand the expression and then equate the coefficients. Okay, thanks for watching, and let me know if you've got any questions.